Assalamu alaikum. Ladies and gentlemen, for our final year project, we opted for the design and fabrication of a modular slash hybrid prosthetic arm under the supervision of engineer Hamza Toor. With that being said, my name is Bilal Siddique. Joining me are Ali Anwar and Majeed-ullah Khan, and today we'll be going through how we executed our project and the results that we achieved.
Assalamu alaikum. My name is Majeed-ullah, and I will start from where Bilal left. Taking a look at Pakistan's low-income earning labor class employees, we see that for them, traumatic injuries are very common due to the lack of safety protocols. One very common injury that severely handicaps them, their livelihood, is an amputation. Amputation can also be caused by a variety of reasons, such as congenital defects, vehicular accidents, etc., in order for them to be able to earn livelihood as they did before an amputation. They require a prosthetic device, however, the Pakistani market forces them to uh, opt for a more passive cosmetic one rather than highly functional ones due to their cheaper cost. That is why by designing a modular and hybridized prosthetic device, we aim provide another option to these individuals that is not only functional but is also a lot more cost effectively durable and serviceable. This leads us to our problem statement, which is that most prostheses have limited and are flawed functionally due to poor design. At first, we had hoped to deliver a hybridized and modular prosthetic arm that would be controlled via EMG signals acquired from the amputee. The arm would have been battery powered and custom fitted to the amputee's needs. Lastly, it would have been capable of performing basic activities of daily living. However, as a result of the coronavirus pandemic and the limitations it brought, we were forced to instead option for a hybridized and modular prosthetic arm that would be powered directly via an AC to DC source and would use a digital PWM pulse to function. It would also abandon the custom fitting aspect due to the lack of an amputee. The arm would still be just as functional as planned, but would only work as a model and not the actual product. For our literature study, we focused on the following topics to get a better understanding as to how we can approach the project and the problem statement. The topics that we covered include prosthetic devices, fabrication techniques, sensor and actuation technologies, material analysis, fabricated and machined metals, actuators. Our step by step methodology to get results first required that we develop the necessary skill set. Next step was to acquire all the equipments and materials and then use them to create the first prototype. After sufficiently testing the prototype, the components were then implemented into the finalized model. This block diagram highlights the key components of the original projects. The two core parts being the amputee and the arm. The arm would be the source of the control signal that the microcontroller will use for actuation. The prosthetic arm, on the other hand, would comprise of three elements: the coupling elements, the connecting elements, and the terminal end. The coupling elements would be a transhumeral socket with the embedded electrode, as our amputee was of this category. The connecting element would be hybridized in the sense that it would be constructed using different materials best suited for the job. Lastly, the terminal end would be modular as it would feature both anthropomorph- anthrop- anthropomorphic and non-anthropomorphic rest attachments. Finally, after prototyping and testing, the amputee would then be trained to use the prosthetic arm. Now, due to the pandemic and subsequent lockdown, we were forced to make some alteration. The lack of an amputee forced us to opt for a digital PWM signal instead of the original EMG, one for actuation, and secondly, we were unable to test out our prepared coupling element. As a result, the aspect of training the amputee had to be dropped as well. However, we do hope to resume and complete the project as soon as the lockdown is lifted. Thank you very much.
As per our original plan, we had hoped to achieve the following results: a battery-powered, EMG-controlled prosthetic arm that would be both modular and hybridized. The arm would be custom-fitted according to the needs of the amputee, after which they would be sufficiently trained on how to use that arm and then would demonstrate its functionality. Let's discuss the actual results. The figure that you see right here is the complete assembled prosthetic arm. We have the non-anthropomorphic aluminum gripper at the terminal end. The connecting element includes the wrist servo, the 3D printed upper arm that features mounting points for an Arduino or a servo bed if we wish to use the anthropomorphic attachment, and lastly, at the end, we have the elbow servo attached to the upper arm using aluminum U brackets and bolts. Furthermore, we have used aluminum horns for each individual servo, as operation at high torques can grind the regular plastic ones that come with it. Now our prosthetic arm provides actuation at three distinct joints: the gripper, which provides the user with an opposing grip; the rotatory wrist, which rotates in both the clockwise and the anti-clockwise direction; and finally the elbow, which can perform both flexion and extension. Since both the gripper and the wrist use the same digital servo, namely the DS3235 270 degrees model, they both have similar performance. Through testing under different conditions, we have calculated how well the servo performs. The DS3235 shows varying performance at three different voltage levels, that is 5 volts, 6 volts, and 7.4 volts. For the sake of getting the best performance, we operated this servo at 7.4 volts and 2.3 amperes to get a maximum torque of 35 kilograms per centimeter at a speed of 0.11 second per 60 degrees. We also observed that this servo is a highly accurate servo in its movement with a dead band of only 2 microseconds. Lastly, before fitting the servo into the arm, we set it at 135 degrees so that it could provide 135 degrees of motion in each direction in 1 degree of freedom. As a result of our modular design, we also have the option to attach an anthropomorphic 5-fingered hand. To actuate each finger, we use the servo bed in which we fit 5 MG996R servos and a sixth servo at the wrist. Each servo is connected to a single finger using high performance, no memory fishing line so that torque is transmitted without any loss or fracture. Again, through testing, we found that the MG996R servo shows varying performance at 4.8 and 6 volts. So for the purpose of maximum performance, we operated these servos at 6 volts and 2.5 amperes. At this rating, the servo output 11 kilograms centimeters of torque at a speed of 0.14 seconds per 60 degrees. Furthermore, we achieved 3 degrees of freedom at each finger with a motion of 180 degrees. Since this is a hobby servo, it has a larger dead band of 5 microseconds. Lastly, we have the elbow servo. Since this joint experiences the largest amount of force at the greatest distance, we opted for a servo that could not only exert enough torque to lift objects at the terminal end, but also be fully capable of lifting the entirety of the arm simultaneously with ease. The servo model is RDS 5160 270 degrees model, where the R stands for a robot servo as it has a characteristic axle at the opposite end of the main gear to allow for the attachment of an aluminum U bracket. This servo also shows varying performance at different voltage levels, namely 6 volts, 7.4 volts, and 8.4 volts. However, due to the limitations of the buck converter used for supplying power, we operated this servo at 7.4 volts and 5 amperes. This is still more than enough as the servo outputs 65 kilograms centimeter of torque at a speed of 0.15 seconds per 60 degrees at this rating. It is also a highly sensitive servo with a deadband of only 3 microseconds and gives us 1 degree of freedom at the elbow joint with 135 degrees of movement in each direction, as this servo too was fixed at 135 degrees during assembly.
Assalamu alaikum, my name is Anwar, and continuing from where Bilal left, in this slide there are three figures. The following figures show how the prosthetic arm is powered and controlled. On the left we have an AC to DC power supply. In the middle we have a control board that regulates input voltage and outputs our desired voltage level. The control board also has three rotary potentiometers that create a signal to help us move the servo motors. And finally, on the right side, we have the Arduino that converts the signal from potentiometer into PWM signal that then actuates the servo motors. For our power source, we repurpose an AC to DC desktop PC power supply, as it not only has high power output of 210 watts, but also outputs voltage at three distinct levels. For the sake of our component, we use 12 volt 12 ampere outputs twice. That is one for each step down buck converter. The buck converter allowed us to step down both current and voltage to our desired level as per the requirements of the servo motors. Now there are two type of buck converter we used. First, the XL4016. It's a DC to DC buck converter that outputs at a voltage range of 8 to 40 volts, with current ranging from 0 to 8 ampere. We use this buck converter to power our elbow and wrist servo motors. An Arduino by setting it to output 7.4 volt and 7.5 ampere of current. Since any higher would exceed the specification of the regulator, we use the LM2596 buck converter to power the gripper servo motor at 7.4 volt and 2.3 amperes. The LM2596 is also very capable as it can output a voltage range of 7 volt to 35 volts with currents of up to 3 amperes. Finally, to control the actuation of servo motors, we use an Arduino Uno and three rotary potentiometers, each of which correspond to one servo motor. The Arduino maps the potentiometer rotation to the servo motors and then actuates it. Now, for the potentiometers, we tested out three different resistance potentiometer, namely 1K, 5K, and 10K. The 1K, due to its shorter range, caused the servo to jump rapidly back and forth, while the 10K potentiometer made the motion extremely slow and drawn out. The 5K potentiometer turned out to be the go-to potentiometer for our project because it provided the perfect balance of control over speed and force. Furthermore, the Arduino is powered via the power jack as it can receive larger voltage inputs through it and also enable us to maintain a common ground with the original power source. In conclusion, we were able to create a modular and hybridized prosthetic arm that has three degrees of freedom and both anthropomorphic and non anthropomorphic terminal ends. It is not only cost effective but durable and easy to repair due to simplified design and materials we used, but is also fully capable of performing a variety of activities of daily living with ease due to the high performance servers we used in it. Following are some of the complex engineering problem attributes attained through the course of this project. And here are the sources used for the preparation of this presentation. This concludes our presentation. Thank you very much for your patience. Stay home, stay safe. Allah Hafiz.